Hi everyone, thank you for supporting this workshop. In this presentation, we are going to discuss the acceleration of fractional Fourier transform via tensor-train decomposition. Fractional Fourier transform is a generalization of the ordinary Fourier transform. It is of utility in every area that ordinary Fourier transform has shown what it can do. In this presentation, we go through things that have interested us and the possible realization of fractional Fourier transform with Tensor-train. We use the following definition of fractional Fourier transform with linear integral transform. However, unfortunately, the above defined integral can be rarely evaluated analytically. A preferred method proposed is fast digital computation without directly computing the Fractional integrals. With convolution computed with faster Fourier transform, the overall complexity is reduced to big O and log n. Seems pretty good. What is the problem then? The problem is the oversampling of the continuous fractional Fourier transform due to the ineffectiveness of non-equal sampling criterion. The vector dimension will be so high that we cannot even afford the complexity of big O and log n in such situation. As for arbitrarily large discrete Fourier transform, performing FFT is difficult for parallel processors for the reason of memory bandwidth limitation. The challenge is even bigger in this case of fractional Fourier transform. Enter Tensor-train. Tensor networks enable a numerically reliable way to tackle the high-dimensional issue of this problem. As a special case, Tensor-train is able to represent high-dimensional tensor by a collection of smaller cores. Leveraging the promising expressive power of Tensor-train, we apply it to the proposed method, in which Tensor-train is used to reduce the calculation with respect to Hartmut product. It is expected that our proposed Tensor-train format can further accelerate the digital computation of fractional Fourier transform. We can also see that continual fractional Fourier transform actually depict the propagation of light. As light propagates, its distribution evolves through fractional transforms of increasing orders, passing through ordinary Fourier transform. In this way, optical realization of discrete fractional Fourier transform can be realized by both classical and quantum optical systems. However, yet the precision and accuracy are not yet there. Thus, tensor network is a practical approach in learning fractional Fourier transforms.